Thanks for inviting me here. Thanks to Mohan. Thanks to Kevin, everyone. It's good to be here, seeing familiar faces back among friends in a way. For those of you who don't know me, my name is Valliappa Lakshmanan. Everyone calls me Lak. I used to be at the National Severe Storms Laboratory. I did research on short-term weather nowcasting. So did a lot of work on pattern recognition. Before machine learning became a thing, we used to call it pattern recognition. So did quite a bit of stuff around algorithms for severe weather nowcasting, etc. So I have a relatively unusual path to Google. And I think this is kind of related to what my talk is. So I'll just talk about this a little bit. So when I was at NSSL, a lot of the work that I had done basically involved image processing and pattern recognition. So for example, this is one of the things that my group did, which was to basically clean up radar images, remove biological artifacts, AP, and all of those things. So when you look at a radar mosaic now from MRMS, for example, this is the neural network that's basically been applied to it to clean up the radar data before it basically gets mosaicked. But a few years ago, but 3-4 years ago, I realized that deep learning fundamentally changed what was possible in the realm of images. It's also in speech and text, etc. But again, my entire research background was in images, and deep learning fundamentally changed it. So this is a pretty famous picture that basically looks at what different layers of a deep neural net do. And it turns out that the very first few layers find things like edges, things like ridges, things like hot spots, cold spots, etc. And then the later and later layers start to put those individual things together to basically build higher level features to the point where the final layers are basically identifying things like faces and cars and elephants, etc. The thing is, somewhere in here, in the third layer or so, it basically starts to find textures. And that was what my PhD was about. So I spent 4 years doing a PhD, basically creating image filters to find textures to basically do a variety of things. And a neural network essentially learns it in a few hours. And so you basically have to say, okay, it's fundamentally changed. This thing where you're doing things manually, you're letting an algorithm essentially learn this from data. The other thing that happened was that at NSSL, we were doing this project called a multi-year reanalysis of remotely sensed mirrors. The whole idea was to basically go back and look at the radar archive going back to '95, and they rerun the Hale algorithms and the mesocyclone algorithms, etc. on it to basically create a historical archive. In order to do that, we basically get the data from NCDC. Now it's NCEI, but at the time it was NCDC. We would get the data, we basically put it all together, and then do it 1 month at a time because we had 70 machines and we had to do them on all 70 machines. It took us 4 years to do this. But then, I basically took a sabbatical, took a 1 year off, joined this company called Climate, and basically my job there was to basically lead a team that built a rainfall algorithm and basically took advantage of both of these things, the ability of machine learning to basically learn things from the data and the ability to basically process large data sets very quickly. So the thing that took us 4 years to do, to go through all of the radar data from '95, it took us 4 years at NSSL, it took us 2 weeks at Climate. So we did it every 2 weeks, and essentially all that we did was that we went through every paper that had ever been written on precip and implemented it and added it into an ensemble and basically created a better rainfall algorithm out of it. And so year was up, sabbatical is done. I said, let's move back to Oklahoma. And my family said, you go, we like Seattle, we'll stay here. So I had to basically decide what else to do. And so, where would you go if you wanted to be part of these two revolutions? There's one revolution in terms of machine learning, of this ability to learn things from large amounts of data very quickly, and the ability to process data at scale right? In a way. And to me, I think the answer was pretty obvious. Google was it. So let me just talk about both of those revolutions, right? And why they're very related to each other, and they get at what gets me really excited about where we are now. And I'll focus on the scientific aspects of this. So in terms of cloud computing, how is cloud computing transforming science, right? What is cloud computing first? Essentially, it is a part of this long-term shift in how computing resources are managed, right? It used to be that we had, when I first joined NSSL, I had a machine under my desk, right? That was my machine. Nobody would take it away from me. And then at some point, 10 years later, right, the IT department came by and said, nobody's going to have machines under your desk. We're going to put them all in data centers. But the data center was on floor number 3 of the National Weather Center, right? So anybody came on a tour of the NWC, we'd proudly take them to the data center and say, look at all these machines we have, right? And that was basically us owning the data center. But then the next trend, and that's something that hasn't quite happened in science, is this idea of having a virtualized data center. So why basically take up one entire floor of the National Weather Center to host machines, put it somewhere else, and have more conducive uses of your space. And that's the virtual data center, where it's still your machines. You're still installing software on it. The only difference is that it's not in your premises. It's somewhere else. Somebody's basically managing physical access to it. But that is fundamentally uninteresting. Instead of you running the machine, somebody else is running the machines. The final, right, what people call Cloud 2.0 is essentially this whole buzz about serverless. This idea of being able to say, this is my code, I want you to run it for me, and let the cloud provider figure out how to run it, how many machines to run it, how to auto-scale the code, etc. So I'll talk about that a little bit. Okay. So in terms of what benefits does cloud computing bring to science, there are 4 benefits. The first one, probably the one that gets most people excited initially, is lower cost, right? So let me just show you what I mean here. The idea is that you can go to any cloud website, and this is true of all the clouds, all whether it's AWS or it's Google Cloud or Azure. You can basically go in and say, well, I want for myself a compute engine. I want a VM instance. And then you can go into the VM instances. Okay. So let's say, well, this is very small. Okay. Better. Okay. I'll go ahead and say I want to create a new VM instance. And we can basically say where we want to create this instance. And you notice that we can basically pick any region. It tells you how much it is. And you can basically say, I want to create a machine with 8 CPUs. So fine. That is one way to think about it. But a better way to think about it is, I have a job, and my job requires 6 CPUs and 16 gigs of RAM, and go give me a machine that gives me this, right? And we may not actually have a machine in our fleet that actually has 6 CPUs and 15.5 gigs of RAM, but you basically pay for that, right? And this idea is that you think of a machine as this virtual thing. It's not a physical thing anymore, right? And you can basically say, you can attach GPUs. You can basically ask for a specific type of processor if you wanted it, and you could create it. You could basically go ahead and do that. That is one aspect of creating a machine, but that is extremely low level. At this point, it is no different from you running your own machines, right? You basically, all that you're doing is you're renting machines. A second aspect is to say, well, I want a machine, I want a VM in which I can run TensorFlow. So what I'm doing is that I'm basically going in here and searching for TensorFlow. It's called Cloud Launcher. And we now get a set of pre-configured machines by a variety of third-party people that has TensorFlow installed on it. So you could basically go down here and say, well, I'll go ahead and take the Bitnami thing, right? And I can launch this on Compute Engine. It's going to cost me $14.20 a month, right? You probably are going to use it for a few hours, and you will pay for those few hours that you use it. So you could get bare metal, or you could get something with the exact software that you want installed, right? So that's when you think of cloud, that's kind of what people think of initially, right? You think of, I can go get a machine. It has the software that I want, and I can go use it. Okay? And this by itself is actually pretty cool because as you saw on those prices, it is, you tend to basically run things that you're doing for a few minutes at a time. So you're essentially paying a few cents. So that essentially means that the cost of a cloud computing job is incredibly cheap, right? We don't make our money from scientific users, okay? We make our money from the big commercial people running like tens of thousands of nodes. But here's an example of like a cost per genome, right? This is basically year on year, how much does it cost to sequence a genome, and basically where something used to cost $100 million, I mean, the y-axis is logarithmic, right? And you basically see the improvement in computing power. That one big change in inflection point is a new method. So forget about that, but other than that, it's pretty linear in logarithmic space, and then finally, it plateaus out, and at this point, it's essentially just administrative cost, right? The compute cost is negligible. It's a round of error. It's just the cost of like administration and like salaries for the people doing the work. Okay. The other aspect of this is that there are all of these connected devices that are coming out, and this is particularly important in atmospheric science. Okay. In 2017, there were 8.4 billion connected things that came online. And this is something that just wows people when it's safe. But it is, I mean, most of it is in manufacturing. So when you look at where is a lot of ML going on, where's a lot of cloud computing going on, it's an Internet of Things. It's basically in the manufacturing space. But what this essentially means is that sensors are ridiculously cheap, right? So sensors are getting ridiculously cheap, and as atmospheric scientists, right, one of the things that you should be looking at besides cloud computing, besides machine learning, is this third aspect, that sensors are getting so much cheaper and ubiquitous, and you can actually get data from wherever you want it, okay? So, right, so cloud, right, as I said, could be rented infrastructure. You could just go get the machine that you want, install it, but that's really, really, really boring. That's the old way of using cloud. The better way, right, is to think of some of the other benefits that it gets. So sure, you can get lower cost, but let's look at some of the other things. The other big change that cloud gives you the opportunity to do is repeatability, right? The things that you do, how can you basically make it repeatable, right? And there are two aspects of it, right? Any research project involves software, involves data, right? I just showed you Cloud Launcher. You have a VM. I said I want a VM with TensorFlow, and I got a VM with TensorFlow. It doesn't have to be just TensorFlow, though. If you do a research project and you've installed a bunch of different software of some specific versions on it, you can go publish that particular VM, right, on Cloud Launcher. And anybody who wants to repeat your experiment, they don't have to do anything else. They could just go get the VM, right? But of course, you don't want to publish VMs because those are very heavyweight. What you really want to publish are container manifests, Docker files, right? Which is, again, one more level of abstraction above a VM, where you're basically saying, the problem with the VM is that it's a VM with specific hardware configurations. A Docker file is essentially a list of all the software that you need that somebody can basically run regardless on whatever hardware that they want. So it's a nicer way to basically create repeatable software. But the other thing that you can also do is that Cloud Launcher is not just about compute engine, it's also about cloud storage. So one of the things that is becoming increasingly prevalent is to also publish data sets, right? So that anyone can basically go access them. And the cost of storage is ridiculously cheap. So that essentially also makes it a very, very, very easy way to get repeatable, right? And the cool thing is that two things together mean that you're not just providing your data, you're providing your data along with the compute mechanism to actually operate on the data. So that's what makes things repeatable. If you just put data out there and you publish some code and the code goes obsolete, right? Your student leaves or your postdoc leaves, that doesn't do anybody any good, right? This idea is to basically publish the two together, publish the data and the software together. And that's something that, again, this idea of having a cloud gives you the ability to do that. The third aspect, right, is collaboration. Okay, so what do I mean by that? Right, one thing to realize is that when we think of a machine, we think of a CPU and we think of a disk, and the two things are attached to each other. Right? With cloud, they're actually separate. Okay, so you basically have your processing being run by compute engine or EC2 instances or something like that, and you have your storage, which is basically done by Google Cloud Storage or S3 or something like that. And these two are completely separate things. So you can basically have your data on cloud storage, and then you can spin up a new compute engine VM, and it can access that data, right? But wait a second. You don't have any data local to the machines that you do the processing in. This is fundamentally different from the way we normally think of things. We think of data stored locally to the disk, right? Forget about disks, right? Disks are so 1990s, right? Think of this data being stored in a cloud storage, and the network connection between the cloud storage and the compute engines, it's a petabit bisectional bandwidth network, which means that any machine that comes up can access any data that it needs at blazingly high speeds. Okay? So it's essentially the equivalent of, if you have 100 machines, it's the equivalent of 100 gigabits per second. Right? Fast enough that you don't have to worry about copying the data locally to the machine that you're doing the processing on. Right? So just go ahead and read the data directly off cloud storage. And so you can basically do your analytics whenever you want, right? And you can access the data in place. So that's the key way to think about it, right? When you're working in terms of a cloud mechanism, you're thinking of accessing your data in place without moving it. So what does that give you? What is this idea of you have your data and you're spinning up machines on demand? What's the benefit of this? Okay? So let me show you this example, and I'll leave you links for this. So this is this is a code lab. So it's a set of instructions that basically walk you through doing a particular job. So in this case, I'm basically going to do this job where, let me just go ahead. Okay. So I'm going to basically run this query. So I'm going to a web page. So this is what I'm doing. I'm going to a web page. And on this web page, I'm basically saying compose a query, and I'm typing in a SQL query. This SQL query is essentially pulling data from the equivalent of a storage bucket, right? And I'm basically saying go ahead and pull some data, pull the complaint type. So this is from New York 311 complaints, and order it by the number of complaints. So we do this, and 3.3 seconds later, half a gig of data has gotten processed, right? And we basically get back that there were 230,000 complaints about residential noise in 2017. Couple of things here. We processed a humongous amount of data. So this 3 seconds, 5 seconds still holds up to a few terabytes of data. Right? You'll be able to basically do a query and search and find and do whatever you want on up to a few terabytes of data. It's going to take you just a few seconds. How does that work? It's because when I ran the query, thousands of machines essentially came up and basically split the data among them, and each of them processed a little bit of the data, and everything got combined. So there were like multiple stages that happened, and we basically got back our results. Right? So this is what we mean when we say something is serverless. Right? Notice that I was able to analyze my data without ever spinning up a compute engine VM, without ever installing software. Right? There's none of that. Right? It's some code. In this case, it's SQL code, and it's data that's on cloud storage. Right? And you basically take your code and you say apply it to this storage bucket, and it happens. So this is the way you want to organize your code. Okay? that is the only way you get this kind of massive scale. And because the ultimate reason that this works is that the economics are like this, right? Whether you run 10 machines for 100 hours, or you run 100 machines for an hour, or you run 1,000 machines for 6 minutes, or you run 10,000 machines, you get the idea, right? It's going to cost you exactly the same. So why do you want to wait 10 hours or 100 hours when you can get your results back in a few seconds? So that's basically what is exciting about this. The second aspect of this is what I'm doing here is that I'm basically on the x-axis is daily temperature, that is from a NOAA data set, and the y-axis is the New York City data. And the cool thing about you never having to move data around is that you can actually do analysis on different data sets from 2 different providers and combine them on the fly. You can combine the data on the fly and do analysis on the fly because all the data is just there, right? The only thing that you need to do is to basically make sure that you have access rights to that data. So, number one, it's serverless, right? I didn't need to download data. I didn't to work with it. The data is already there. It was based. I was able to run an ad hoc query. I ran it at tremendous scale, and I was able to run it on New York City data and on NOAA data because the providers of that data essentially made it public. They basically said anybody can access this data, so you can essentially share data very, very conveniently. And obviously there are gradations. You can share it with a particular domain. You can share it with star, that edu, for example. You could do a variety of different things. So what I just showed you was the right-hand side, BigQuery analytics. It's great if you have structured data, right? Columns of data. And you're like, hey, yeah, columns of data are easy. We deal with raster data. We deal with images, right? What can you do if you do images? Do I not have to basically copy data around? And answer is no. If you have unstructured data sets, there's another parallel technology called data flow. The open source thing is called Apache Beam, and data flow is the execution service for it. And what that lets you do is basically take your data, whether they're structured or they're unstructured, whether they're structured or they're images, and you'll be able to basically run your code on it. So that's what this thing does. So this is an example of doing Landsat data processing. There is another one that talks about Go 16 data flow. You can find it. Go 16 data flow, how to process weather satellite data in real time. So this basically talks about, so in this case, what I'm doing is that I'm basically pulling all of the data around Hurricane Maria. And basically, as the hurricane moves, I'm finding each of the locations, and I'm basically taking the satellite data corresponding to it and using it to basically create a movie loop. Is there a movie loop? Yeah, they're creating that movie loop, right? And this entire thing is done without me ever actually spinning up a VM, right? So what I'm doing there is that I'm basically writing some Python code. So there's a full code on GitHub. And the Python code, essentially, where you had SQL code to do structured data, you have Python code to do, so this is the Python code that's basically doing the pi resample. So this should be all relatively straightforward, right? Doing a pi resample to get the closest data, reading netcdf files, and in this case, let me go down to where actual. Okay, anyway, there's a bunch of code here. You can go ahead and look at it. But it is essentially Python code that is getting auto-scaled, right? And when you run that Python code, over time, it's going to basically start spinning up more and more machines. And it's going to basically do, so you see that here, it spun up to 10 machines over time to basically do the processing. So if you're processing large data sets, right? I personally think it's a failure if I have to go down to a compute engine, right? That essentially means that I'm not I'm not taking advantage of this massive scale that a serverless offering can provide us. So that's the third aspect, this whole collaboration. And the final bit is democratization, right? And that democratization part is where it comes to machine learning, right? Bunch of people can do this. So that's the second thing, right? We talked about cloud computing. It's providing all this infrastructure, this ability to run things at scale, to do things without running through a lot of infrastructure things. What is ML? Okay, so I think David's going to talk about images in the next talk, so I decided I'll talk about LSTMs instead, sequence models instead. So deep learning is basically making great advances in two different domains, right? One in terms of images and other in terms of time series data. So if I showed you this time series data, and I said, well, my LSTM machine learning model, if I presented all the data in the blue, it's able to basically do the stuff in the red. You're going to say, well, big deal, right? It's not that that's not that impressive. It's not that impressive because we've always had ways of doing time series prediction. We've had ARMA models. We've had a variety of different things that you could do time series prediction in. But the way this is done is that it's not actually taking into account the fact that it's a sine wave. It doesn't know that. It's basically just learning it from the data. It's just by looking at the sequence of numbers, it's basically being able to predict the next. And that's important because all it cares about is that you're giving it a sequence of numbers. So if, for example, we give it the text at the top, right, and we show it, so we train the model on text without punctuation and give it text with punctuation as this is what you need to create. Now if we give it something else, it's going to automatically add punctuation for us. It's going to add the commas and the periods and the semicolons to any random piece of text. That seems fundamentally different, right? Punctuating text is actually the same as that. Because all that we're doing to punctuate text is that we're taking every word and we're replacing every word by a number. And now a sentence is just a series of numbers. And we're basically saying, here's a sequence in, here's a sequence out. Neural net, go learn this thing. And it's basically able to do this. And of course, you have gradations of this until the point you get to smart reply. How many of you have used smart reply? You know what it is? Like where if you get an email in inbox or Gmail, it suggests to you 3 possible answers to your email. Right? That is fundamentally this. Right? It's fundamentally this. It's a sequence-to-sequence problem where your email is the input sequence, and those 3 things are the output sequence. Okay? And that's where the magic comes, right? It's just data. Right? You can just train this thing with just data, and it's able to do that. But the cool thing is you can actually combine the two. Right? Your input is a sequence, your output is a sequence. What if your input was an image and your output is a sequence? What if we show the neural net a bunch of images and show them the graphic, the captions underneath it? Can it do something? And this is an actual prediction. You can't actually read this, but given that image, the prediction is a cat lying on top of a rug next to a cat is a first caption. And all of these are actually, the links at the bottom, I think you have the deck. These are all like, the code for all of these is there. So go ahead and look at it, explore the code. So that, the ability of machine learning to be able to do things from just data is just stunning, right? Of course, the amount of data that you're talking about is huge. And for most of the companies I talk to, they step back like 3 steps when I tell them the amount of data that they need. Atmospheric scientists, we have no problem, right? The amount of data is not a problem, so it's kind of it's high time we started doing good things with it. And as an example, right, this is something I worked with Philippe Tissot in Corpus Christi on. The idea was that they had actually flown drones and taken pictures of coasts. And NOAA had actually gone through on every piece of the coast. They had identified the oil spill risk associated with different parts of the coastline. And the idea is that the oil spill risk might be just at that little estuary there, and that's fine, right? We basically trained the machine learning model on thousands of these images. So given the drone image, this is what the oil risk category is. And having done that, we were able to basically run the model and get like about 90% accuracy on a 16 label data set on just finding what this was, right? So this is just one example of the kind of thing that you can do by just having the appropriately labeled data. Another example, this is not atmospheric science, but probably the other field that has tremendous amounts of data is genomics. So, one of the things that's happened is that I now know more about genomics than I ever did, simply because of virtue of the fact that that's a data-rich field. And one of the things that happens is that you're trying to find what are called variants. And that is basically how different is a particular genome from a reference genome. And finding where the variants are and finding where, like what kinds of variants have happened is often an indication of the kinds of things, disease, if you're doing plants, for example, disease resistance is very tied into variants. So being able to do this, but unfortunately, like to be able to find a variant involves finding sequences, and the kinds of variants involve changes, right? You have your original sequence, and the variant is a change in the sequence. And being able to find the minimal set of changes that explain what a variant is tends to be a combinatorially explosive problem. So you solve that with ML, and so that's the next new frontier in genomics is something called deep variant, a way to basically find these things with deep learning. But having done that, right, that is one aspect of it, right? The one aspect of this is the training part. You have your data, and you've trained your model. You have your model, and you're doing prediction. You now have your model. The next aspect, and that's equally important as in atmospheric science, is to be able to make predictions. Like when we created a neural network model to clean up radar data, we couldn't just do it on archived data and call it a day. We had to actually run that model in real time on extra data as it came, right? And the way we did that was that we built this thing called WITS2, which is this humongous C++ software system, and it was like, at the time I left NSSL, it was like something like 800,000 lines of code, right? Massive, massive, massive system that nobody quite completely understood because it had basically grown up organically over time. Fortunately, this need to basically run streaming code and archive code the same way, this is a problem that's been solved, right? In industry, that's what data flow does. It basically, the same code that I did for my Landsat images, that I did for my satellite images, that I set auto scales, it runs both on archived data, the data that's on disk, and data that's streaming in, and it's basically doing the same things, right? So that makes it very convenient to to train a machine learning model and to apply the machine learning model. The other thing to realize is that the only reason that deep learning works is because data sets are huge. So this is another example where the x-axis is the training data size, and it's a logarithmic scale, right? So every line there is a doubling in data size. So so you see the error going down, but the error goes down linearly when your data size doubles, right? So by the time you're out here, you're talking about 2 to the power 27. So when we talk about a language translation model, we're talking about data sets of the range of 2 to the power 27 lines of code. So that's basically where you see the kind of accuracy that we're seeing with our text models. So when you're talking about like what kind of model should I use and what kind of data should I use, the more data you have, the better your model is going to be. And you can use a simple model as long as you have more data. And that's another way in which atmospheric scientists are lucky, is that we have lots of data, so we can afford to use simpler models. Okay. But the other aspect also is that this is again a logarithmic graph. You can hardly see it, but out here is the like petaflops per day of training. Okay, that's a logarithmic scale, and this is the year. And each of these is an image model. So out here is your AlexNet, which basically started off. AlexNet was basically the model that essentially from Jeff Hinton that basically showed that deep learning was possible. To out here is AlphaGo, AlphaGo 0. So, and you basically at each of these lines is a not doubling this time. It's a 10 times, right? The amount of compute power needed. So between AlexNet and AlphaGo, it's 10,000 times the amount of compute power needed. So this basically brings full circle why you do ML on the cloud. So with that, right? So that's basically the 4 key benefits, like cost, repeatability, collaboration, and finally, the only way you can basically do these massive scale ML models is if you take advantage of these kinds of benefits. So I'll leave you with these resources. So many of the examples that I showed you, well, with the Landsat image or with with those BigQuery data set or with the coastline classification, that's all in here. This link basically gives you free educational credits, but you often don't need free educational credits because a free trial often gives you enough. Like on BigQuery, for example, the first terabyte per month is free, right? So as long as you're querying less than 1 terabyte, you can do it every month, and you still stay under the free quota. If you're looking at Coursera courses, cloud.google.com/training. Okay, there's a bunch of courses. In particular, there's a course on TensorFlow. And of course, shameless plug, I have a book talking about how to do data on GCP. That I'll take questions.
Time for a few questions for Lak, and just a reminder, if you do have a question, use the microphones on the table.
30 in the morning. Yes, John.
So I was wondering, are things like Google Street View available also through the platform so that you could, say, do a cross-analysis of one data set of images against like that?
Right. There are some things that are available and some things that aren't. Google Street View in particular is not. Okay, but there are, if you go to Earth Engine, you will find many data sets available. So there are a lot of Earth data sets available, but not Street View. Okay. If you're interested in Street View, come talk to me.
False positives and uncertainties are fine for shopping, but science has a. Do you see any incompatibility between the nature of machine learning and the scientific enterprise, at a philosophical level?
That's a great question, right? The thing is that every ML model is wrong, right? Every ML model is wrong. We know it's wrong. The question is of basically being able to know where it's wrong, or to know the likelihood that it's wrong. But what I would argue is that everything that we're doing today in weather forecasts are also equally wrong, right? And so we're dealing with that. And one good thing with ML is because it's so data-driven, you actually do get uncertainty bounds with every prediction that you make, right? Rather, if you use a set of rules that are derived from a case studies, you actually don't know what the uncertainty is. You're not able to quantify it. On the other hand, if you basically trained your model on a large enough data set, you do, right? You basically can do very traditional statistical things like jackknifing, like bootstrapping, to basically figure out what the uncertainty bounds are. But there are also other, like the nature of ML and the nature of the final layers of your machine learning model actually does give you, like if you're doing a classification model, what the output is a probability. It's not a 0 or 1, it's a 0.7. So that gives you an idea of what the certainty and uncertainty is.
So it might actually elevate scientific discourse away from overly categorical thinking and stuff.
Yeah, absolutely. I think so.
Can you tell us a little bit about what interpretability options are available on the Google Cloud Platform for, like, if you do the serverless deep learning training, right, how can you investigate what kind of features the network learned?
Oh, absolutely. So I mean, the serverless part is only the fact that you don't need to install TensorFlow on your own machines. Everything else remains the same, right? So if your model is exporting statistics to TensorBoard, right, those summary statistics are on cloud storage, and you can bring up TensorBoard and you can view them. So all of the traditional ways that you would troubleshoot your model, whether through evaluation graphs or through loss functions, or by basically looking at the distribution of weights on your layers, all those are still available, right? So that's the first part. The second thing is that you asked about interpretability. There are a couple of very standard ways that people do interpretability. One of them is called Lime, and Lime is actually built into our notebook solution. It's called Data Lab, and Lime is actually built in. So you can actually apply Lime to your model to basically see where it is. So on both sides, so don't let the fact that it's serverless kind of think that you're getting something less. It's exactly the same. It's the exact same code, exact same outputs. It's just that the machines go away after your job is done. So you only pay for the time that they're up, right? And you can submit a job without worrying about installing software or managing the cluster communication.
All right. Thank you.
Okay.
You can come talk to Lack now during the break. I think we're on break now.
Oh, wow.